he has started or not.
Okay. So just one instruction I want to give to this attendees. Can I?
Please.
Yeah.
But
Uh,
make sure that I think he has started the recording.
okay.
Yeah. Okay. Yeah. Please go ahead. You can start now. Yeah.
Okay, sir. Good afternoon, everyone. Welcome you all in the second session of AICTE sponsored ATAL FDP on robotics. A very good course on robotics by Daniel H. Wilson that robots are interesting because they exist as a real technology that you can really study. You can get a degree in robotics, and they also have all this pop culture real estate that they take up in people's mind. It's my proud pleasure to introduce our esteemed guest, Dr. Mangal Kothari, who is the speaker of this session. I welcome you, sir. Dr. Mangal Kothari is Associate Professor at the Department of Aerospace Engineering, Indian Institute of Technology, Kanpur, Kanpur, India. He has obtained his PhD in Control System from University of Leicester. His research interests fall broadly under the area of navigation, guidance, and control of aerospace vehicle. The title of today's talk is Autonomous Multicopter UAVs. I request Dr. Mangal Kothari to continue the session. Over to you, sir.
Okay, thank you very much, Divya, and thanks for pronouncing Leicester right.
I, thank you, sir.
I think you might have contact in the Leicester. Otherwise, people do call it Leicester.
Okay, thank you.
So, uh, good afternoon to all, and let me apologize to say that you are not able to watch or maybe able to look in on my face through the camera, but maybe in the next 1.5 hour we'll enjoy about multi-rotor UAVs. So the session is on the robotics. So I will be giving talk on the multi-rotors, but it will have an aspect of the various aspect of the robotics. So uh, my like one of the research interest is in aerial robotics. Therefore, I will talk about autonomous control, but it will have a resemblance with the ground vehicles that I also do work on. So I do work on the legged robots, and we'll look into different aspects as we'll move. Okay. And thanks, Prasid, for inviting me and giving the opportunity. I am happy to share the information that you are from your college. Two of the maybe you are passed out or alumni is working with me and they are doing really well. So I think Ajit conducted a session a couple of days back. So he's also working with me, and there is another guy, Vinit Menon. He's working on with me. So I think you are getting very good training, and I am really happy with your alumni. Okay, with this, I will start my talk. So, uh, just give the idea what we are working on. Okay, so we are working on number of the aerial vehicles. That is the start with the fixed wing UAV. So you have seen the fixed wing everywhere. Many of you have flown here. So the whole idea is to make it autonomous. So it has a 2 meters wing span. It has a conventional control surface, that is elevator, rudder, aileron, okay, and throttle. We do control and autonomously it can do the loiter, it can do the path following and other aspects. So although we have designed on the 2 meters, we can do for much long wingspan. The other vehicle we have worked on this is a, you can see, boomerang. Okay, it's a remote control. This is a kind of Sudarshan chakra. So you change the angles and then you replicate how the Sudarshan chakra works. Uh, just give me a minute. I'll just pause. Okay, and I'll in 1 minute. I'm sorry, there was a disturbance. So just and this is about with virtual words you cannot control. And then we work on the conventional quadrotor. So quadrotor nowadays everywhere, everyone works. You have seen in the marriage party, college function, adventure, sports, everywhere. So what happens? You have seen the quadrotor, and now if you know how to control the for BLDC, and if you have done any embedded system course like on STM32 or and if you know how this cross tool chain compilation works, you can make your autopilot work. You can control using PWM for BLDC motors. If you have a IMU that has accelerometer, gyroscope and magnetometers, you can measure the attitude, and if you integrate with the GPS, you now have a position and you can autonomously navigate. So if you look into this special vehicle, what happens? There is a no, like you can say, mechanical transmission systems. You have 4 BLDC motors connected with the rods, and you have a smart computer. You can see that single but autopilot. Okay, I'll come back to that. So there are several varieties of the quadrotor are available in the market. But if you look, like especially two products, one is DJI, so it has a different range of product, and then another one is Skydio. So all what they are doing, they are using the 4 motors and one autopilot board. But then with help of that, some people hardly get 5-10 minutes of the endurance, but others are getting hour of the endurance. So there is a magic in the like optimization, design and control things. So some of aspect today we look. Now what happens? Although with the like professional design like DJI and Skydio, they get the large endurance time, but if still we want to push for that, so other type of vehicle is a engine helicopter. So you put gasoline, like old moped you might have not seen. You have a 2-stroke engines. Now one single big rotors, instead of 4 rotors, you run it, you change the blade pitch angles, but here the control actuation is a bit complicated because here is a source plates come into the pictures which control the blade pitch angle as you rotate the rotors, and there are some cyclic things also. So cyclic things like you have some pattern like amplitude of the your blade pitch angle, so that is called longitudinal and lateral cyclic. So you will control the motions, and controlling the yaw angle, that is like on the axis you are rotating. So there is a small rotor in the tail, it has another actuators, that is only that you change the blade pitch angles. And these helicopters are very popular. The reason is that anytime you have a rescue missions, only helicopter will be useful. If you want to do surveillance, you will do the fixed wing, but if you want to save the men, both, so helicopter would be useful. And we do work on variable pitch quadrotor to overcome the limitation of the conventional quadrotor. So what we have do, instead of the electric power, we have put the gasoline power. So now fuel has a lot of density, so we can push the endurance to its boundary. So such vehicles can provide the endurance up to the couple of hours. So what I would request in next now we have around say 80 minutes. If you have any question, please feel free to stop me. Maybe you can virtually raise the hand and I will be happy to take the question. Okay, so these are the some maybe you can see our concept we are trying. So out of what you see left hand side, we have not worked on the lot, but in the right hand side we have work on the quadrotor tail seater. So what in the previous slide I have told that there is a limitation of on the quadrotor, that endurance limitations. So what happens, the reason is that for that limitation, the weight is supported by thrust, and thrust is like you can see expensive to produce, or when I say expensive to produce, because it's require power and you can only carry limited power through your battery. So if one has to increase the endurance, what they can do, they can put a couple of wings as shown in the figure here, and then make this vehicle as a fixed wing type. So when you make it is a fixed wing type, now weight is supported by the lift, and lift is generated by air passing through these two wings. So the thrust requirement only require now propel in the forward direction. So there is a relative motion of air with respect to the wing. So thrust requirement reduces. So your power requirement is reduces and you can fly for longer. So such type of VTOL vehicle has an advantage compared to the traditional, like you can see rotary wing vehicles and fixed wing. If you consider fixed wing, they require runway to take off landing. Even you can do the hand launch and catapult launch and other things, but for landing you require some things. This type of vehicles does not require any runway, so that infrastructure you do not require. And so this is the advantage of any VTOL type of vehicles. And then what happens once it's in the air, it can transition from the typical multi-copter type to the fixed wing. So it has the advantage of the fixed wing type of advantage. So there are many such concepts are being researched and employed in the market. So I'll start with one short video what we have done in helicopter, and then I'll come back to the technical details. So this is a maybe I can this is our autonomous helicopter we have developed at IIT Kanpur. So this is a single rotor. So you can see there is one autopilot board. So autopilot board is known as a PIXOC. It is made on STM32. In STM32, what we do, we have a like RTOS. There are different RTOS is there in available. So we are using NUTX, but one can use free RTOS, Jaifer, and Chibios. And then you have a middleware. Middleware in the programming, you have like a publish subscribe thing. So I think you have been introduced with the rows. So one node to another node. So inter-process communications happen through the publishing and subscribing. So you have a like IMU. So IMU have a accelerometer, gyroscope and magnetometer. So they will publish their readings. And then you have a sensor driver that will take this reading and will create a attitude. That attitude will be again subscribed by your attitude controller. It will use the control like it can use PID, it can use the sliding mode, what is being taught or expertise of the Dr. Prasid Trivedi, or any non-linear control like a backstepping, and it compute the control command. That control command through the your PWM or servos is given through your vehicles, and you fly that. You may have a GPS also, so you read the GPS data. So you have an applications layer, you have a middleware and the RTOS. That all is done for the like PIXOC board. And the good thing is that it's in open source available, so you can tweak the controller if they have given the PID. But if you want to employ the non-linear control or the advanced control, you can do, and you can fly. Apart from the control scheme, there is a frame design also. So you have to design the frame which is robust, okay, which has a less drag, so it can have a good endurance. So you can see that this vehicle is performing a different type of maneuvers, and this is a really aggressive vehicles. So when it has to go forward, what it does, you can assume there is a thrust vector. So that is how supports the weight. When it has to go forward, that thrust vector is a tilted forward. When it has to go sideward, the thrust vector is tilted sideward. So accordingly it will does, and for yaw motion it will generate the force from the tail rotor, and it has a moment arm with respect to CG. So CG is close to this rotor hub, and then you have a yawing moment. So now one of the, you can say, is interest is in the autopilot development. So when we have to develop the autopilot, we require mathematically modeling, because we have to develop the control law based on some models. So we have to develop flight dynamics model. Why I am telling the flight dynamics? Because it's related to flight, and dynamics model, that means how it evolves with the time. So in order to develop this flight dynamics model, you have a kinematics, dynamics. So special that is already available for all the vehicles, whichever in robotics aspect is there. So kinetics relate with the, you can say, position with the velocity, or you can say angular displacement with angular rate. Dynamics is a kind of, you can say, Newton or Euler's laws, F equal to ma. Only things now the vehicle is moving, so it's in the rotating or accelerating frame. It's not an inertial frame, so we have to fix it. Similarly, you have to use the Euler equation for moments. So these are the kinematics and dynamics. Usually it's bit difficult for electrical people, but once we understand, it's pretty straightforward. Then what comes? Rotor aerodynamics. So for quadrotor type of vehicles, what happens? There is a whatever geometric shape is given, we are not changing the any blade pitch angle. Only we are changing the what is our input is the RPM. So we are controlling the RPM. So rotor dynamics become pretty straightforward, and there is a no transmission system. That's why quadrotor becomes very popular. But if you are considering other aerial vehicles where rotor dynamics, where you are changing the blade pitch angle, so that is bit involved. But there are theory like you have a momentum theory, blade element theory. You can use that, and you can say that how thrust is produced, how moment or torque is produced, and that the thrust and moment will go into the dynamics, that will change the velocity or angular rate, and that will go into the kinematics, that will change your position or angular displacement. And then when you take from the sensor, okay, what is the current position and what is the desired position, and you compute the error and come to the control design. So now when you have to do the control design, what you do, you look into the maybe linear control first. So in linear control we have a different way. So PID, majority of us do the PID. So we can live with and without model. If you do not have a model, you don't have to worry. You iteratively, or you use some gain choosing techniques, and you choose the gain and you fix it. And if you are expert pilot, or you have a luxury of hiring the pilot with his flying experience, you can choose this. So it's a model free or model based also. You can do the PID control. Another approach is pole placement. Who has done the state space control course, that you have a matrix A and B, and if you know where desired pole is required, you can compute the A minus BK, and then you can compare with the correctest polynomial, and you can find the gain K that is supplied to the controller. Alternatively, if you are interested in LQR, you can use JB Hamiltonian equations, and then you can solve the infinite or finite time regulator. But would you prefer the infinite time regulator problem, because then you do not have a differential Riccati equations? So these are the techniques you might be aware, or it would be discussed in this workshop. Some people would prefer to use the nonlinear control design compared to the linear control. The reason is that, see, in the linear control, you have like whatever control design you choose, that is only valid for the certain flight regime or operating range. In nonlinear control design, you choose the whole control structure which is valid for the whole flight envelope. So you prefer, but then there are like concept like pole zeros are not available, roots are not available. So you need a different mathematical tool to understand that. So in nonlinear dynamic or nonlinear control, the most popular is a nonlinear dynamic inversion. So what you do, this dynamic inversion is you can say link between the linear and nonlinear control. So you choose a nonlinear control and cancel out almost all nonlinearity. If you see theoretically, you cancel out the all nonlinearities, and resultant closed loop system is a linear system. So whatever you property expect from the linear system, you can, from the closed loop, you can accept that. But then your control demand will be high. So you would prefer to use a backstepping type of control, where you could keep some beneficial nonlinearities, but then you have to have a model in the stick feedback form. But majority of the system, what do we work, they are available in the stick feedback form, mechanical and aerospace engineering. So if you do systematically design, you can have a robust control, and you can retain the beneficial nonlinearities. Otherwise, you can do the sliding mode control. It is a very powerful control scheme. It is robust, but then it has its own issues like chattering. But there are way of mitigating the chattering. You can handle with that. And some people will prefer to use adaptive control. The reason is that, see, there are uncertainties. Although we model the rotor dynamics, but we assume some simplicity. So one of the approach could be that you on the go, unlike your deep learning algorithms where you have a supervised learning, we will be doing here online learning. So you have some weight update law, and then either you can directly control or you can have a direct or indirect control. So you can learn the unknown dynamics and then use that unknown dynamics to control the design, or you can directly use that whatever the uncertainty you are learning for control design. So there are different ways. Uh, some people prefer model predictive control. So the reason is that it has like a derivative type of actions. You are predicting in the future what is going to happen, and based on your future prediction or behavior in that, so your future is secure. You are going to take actions right now. And apart from that, now there are a lot of emphasis on the learning based design. So one is the iterative learning. So usually when we design the control law, we assume the simple dynamics. The reason is that we get the closed form solution, but when we implement that, there are errors. So what you do, based on that errors, you update your control law, and you keep doing that in some way. So you learn your like control learns to deal with the uncertainty in dynamics. So there are approach of iterative learning. One can employ the optimal control, like you have a direct programming and you come with some control in terms of the polynomial, and then you do the flying and you see there is a from the target value, like it's kind of supervised learning if you have a background of in the neural network or or machine learning. And whatever error is there, based on that you update your control law. So you are changing the structure of your control law. Might be you are changing the structure, or you are changing the coefficient if you are using the coefficient based control. Reinforcement learning, it has come from the, you can say, control people to try to solve the like a dynamic programming. So reinforcement, you can say inverse of that. You give the award. So there is a no supervised, no teacher. So you choose a policy which earns the maximum reward. So you want to maximize the reward. So you choose the policy, and what good things about that, you can embed here the control constraint, and then you through the maybe deep learning or with help of the Q learning and other methods, you come up with the optimal policy, and then they use for control. And deep learning now is a favorite topic for many things. So this is all about control. But doing the control, what you require to estimate your attitude. Without attitude, you cannot apply the attitude control. So there are different attitude heading reference system is available. So the simplest one is a complementary filter. So for aerial vehicle, what you do, one set of the estimate you get from the gyros, okay, that angle, and another set of estimates from same value you will get from the accelerometers. So what you say that okay, gyro is a good in the for instantaneous values, and the accelerometers based on sensor properties, you know that it is a good for the in average sense. So you use a combination of low pass and high pass filter. So that is a very computationally, you can see like efficient way. So that filter you use, and you make a attitude, pitch, roll, and angle. Or alternatively, you can use the Kalman filter, Bayesian framework, and then you have a belief of each state's attitude. We require the position estimation also. So from the GPS, we'll get the position. We again use the some filter, but we can have a tightly couple or loosely couple. So the difference is that you can use direct the pseudo range into your filter state, or you solve the from the pseudo range you solve the position things, and then you club with, or maybe you not club, you use that into your information. So there, whatever I am talking here, there are a lot of things involved in that. So that's why I am giving the background, so you'll get the whole pictures. And we may have to operate in GPS denied environment. So how do we operate? So where are the applications? So when I say waypoint navigation, it's not applications. So you have a surveillance type of things and other things, so that your mission is given in terms of waypoint. So it involves in many search and rescue. So the vehicles should be able to follow that waypoints. You want to do the payload delivery, maybe for medical purpose, or HADR, humanitarian aid, or disaster relief, human tracking. So that also slung load, again payload delivery, and swarm. Swarm is nowadays again become very popular. So towards the end of my presentation, I will discuss about that. Now coming back to the little mathematical, lot of technical details or maybe background I have given. So you might have seen such quad rotor, and that is experimental platform. So what is the idea? Each rotor generate one thrust. Okay, that is a perpendicular to the plane of the rotor, and there is a torque. The torque is generated because you are dragging the rotor in the air. So there is a some drag force is created. When it's multiplied by the momentum, it can generate the torque. So each rotor generate one thrust. Okay, that is come from the lift, and another one is a torque. So using that combinations, you stabilize the vehicle or you make it to move forward or in the sideway direction. So to understand this, now when we want to develop the mathematical model, we require coordinate frames. The reason why we want the coordinate frames, like see Newton's law is valid in the inertial or non-accelerating frame. The body velocity or maybe the thrust works in the body frame. So as I told, it is a perpendicular to the your rotor frame. So they are in a different frame. And if you are using the camera for estimations, it will have a different frame. If you are using the lidar, your point cloud will be in the different frame. So for example, lidar will give the point cloud in the lidar frame, and camera is looking into different frame. So you have to project this different quantity into the same frame for decision making. So we need apart from the dynamics, from sensor perspective also we require the different frames. So what is the basic things? So you can I have simplified or maybe I have complicated, I don't know. So two frames, see, you can see V1, V2, V3. This is a one frame, and another frame is that this body frame B1, B2, B3. So you can in one go you can come from one frame to another frame, or you can take the sequential rotations that come from the Euler's theorem and you come into the one frame. So if you whatever you do, this you'll get this directional cosine matrix. So if this angle is known to you, you can play with this, or you may know the relative rotation of that. But then it's a difficult to compute. So there are different way of representing this. So I'll start with the rotation matrix. So that give rise to the your geometric control. So that means is that rotation matrix is the evolves on SO3. What happens when I say that rotation matrix determinant is 1? Okay. So whenever you rotate, you have a spare of the, you can see kind of SO3, special orthogonal group. So if 9 element is there and the transpose is equal to the inverse, and it does not have a singularity. It has 1-to-1 and 1-to property. So any ambiguity is not there. But then you have to play with the matrix. So that requires your differential geometry. So and we are not very happy with the matrix or maybe matrix differential equation. If someone gives us the ordinary differential equations, we are happy. If we have to solve the matrix differential equation, it's not convenient for us. So now people are doing this. Okay, so but still it's not that much popular. It has some complexity, but if once you learn something's basic concept, you can easily implement that. So mostly commonly used representation is the Euler angle. Why Euler angle? You have a physical intuition. So you know what is happening. See, I keep talking from the beginning of my talk. There is a pitch angle, roll angle, and yaw angle. But when I use the matrix, I cannot talk about this. This is a 3x3 matrix. So Euler angles give me the freedom. So what it says that from the one frame to another frame you want to go, you use some sequence. So for the fixed wing community or maybe aerospace UAV community, they use the 3-to-1 sequence. What does it mean? 3 means first rotation you apply along the Z axis, that is your yaw angle. The second axis you choose along your pitch axis or along the Y direction, that is theta. And third axis is along your roll, that is along the X axis or along your nose. And you do 3 rotations from the inertial frame to the body frame, and then you align along the body frame. So if you do this 3 consecutive sequence, you will reach from the your inertial frame to the body frame, or you can come from the body frame to the inertial frame. And this way gives us the physical intuitions. When I say pitch angle equal to 45 degree, what is happening, or if it is a roll angle equal to 15 degree, what is happening. And many times what happens, we are not applying this all three rotation together. Like if I am in the forward flight and I want to go or left or right, I usually turn my I roll or I do the bang. So only I apply the roll angle. So there are other angles are not involved. Only there is a coupling, but they are not directly involved. So it's give me a clear and neat and clear understanding. And moreover, the equation evolves on the like Euclideans, like it's in vector space. So easy to understand, like I can write error, and these are the all ordinary differential equations, may not be linear. We can linearize and we can play. But what happens, there are other parameters, parameterization like quaternions, they are also preferred. The reason is that, see, when you are doing the sensor estimations, so when you do the Euler angle and in your computations, this one thing is that the way it has been divided, it has a singularity issue. So singularity means that if you go through a particular angle, for example, for 3 to 1 sequence, you do the theta equal to 90 degree. When you represent your rotation kinematics at theta equal to 90 degree, that is not well defined. So that give rise to the singularity. So you want to avoid. So you want a similar parameter like Euler angles, that is a quaternions, like in the like a kind of vectors. But now to resolve that, there is a one additional you can say component. So instead of 3, you have a 4 components. So you resolve that singularity, and then again, because quaternion represent the special way of evolving systems, so do not evolve on the Euclidean space. But good thing is that we can approximate in that, and we can play with the quaternion. So just for your information, there are other parameterizations also, classical and modified Rodriguez parameters, and there are axis angle representations that will give idea for choosing here. And the other thing what I was telling, that in Euler angle you have to play with this cos and sine. So that are usually computed in the autopilot using the Taylor series. So you do, or there are inaccuracies shipped into the systems. So if you want to resolve that, quaternion is a good choice. So there are no cos and sine is involved. Okay. So in these lectures, I am not deriving these equations. So when you do this, all the things what I have talked in the last 15-20 minutes, what will happen? You will get such kinematics. So this is a like position kinematics. This is a like rotational kinematics, and this is a kinetics. Okay, kinetics is nothing but dynamics. You get how UVW evolves dynamics, and this is a rotational dynamics. If you are from electrical engineering and you have understood or you have read the static space method, you should be very happy. Someone has already provided you a mathematical model where my control input is TLMN and states are XYG, that is a position, phi theta psi, that is a attitude, roll attitude, pitch attitude, yaw attitude, UVW is a translation velocity, PQR is a rotational velocity. Okay. Now bit of the rotor dynamics. So you may not like it, but still we talk. So what is it like assumption is that, say you have you from the infinite you are taking lot of air, and the rotor works as an actuator disc. So it is accelerating things or pushing down. So if you, simply you can assume, like if you assume that action reaction, so you are pushing down the air, you will get the thrust. But systematically, if you have to do, the air is continuously pushed downwards, so you have to use the mass conservations. So infinite you will have this. Now at the A2, the say actuator disc, you will have Vi, and if you downstream you will have this velocity. So you can mass flow rate you can equate. This is like a Newton's law. We usually see m dv by dt, but now we are looking into m dot omega. Okay, and now m dot we know, omega I we can compute using balancing this, and energy is also conserved. We'll equate this thrust into velocity equal to this energy. So we'll get this thrust and the torque. Now you look into, see, CT is some coefficient. If you are not changing the blade pitch angle, this is constant. Rho is air density, A is area, R square is radius square, and omega square is like your RPM. So if you see, thrust is proportional to RPM square. Although there is a non-linearity, but this is a constant. If you are not changing, you do not have to worry when you are not changing the blade pitch angle. So Q is proportional to omega square. Okay. So while doing that, I have changed the omega because it was convenient to write, and that is what you have to control using your BLDC or motors, this PWM. So TLMN for the quad rotor, you can write this is your control mapping, and this is very important for autopilot design. This is very important. Why I am telling? Let me say. See, if you are writing your code in MATLAB, U is U has come some value. Okay, so that is U is TLMN. So you know that TLMN is T is a say you have come with the 20 Newton. When you give in the autopilot that 20, see, it does not understand. We understand that your what is a unit, but your autopilot does not understand the unit. It understands only 20. Now that 20 newtons you have to generate that mapping. This mapping you have to be very careful. How does you design? So what you have to do? You have to do the scaling. So scaling is that based on TLMN, whatever servo is there, your motor, or if you have a PWM or you have a servos, how much input you will give. That is, you can assume that you have your PWM from the 0 duty cycle to 1 duty cycle. How much, if you gave between 0 to 1, how much Newton it is going to produce. So although these are the numbers, that scaling you have to do, and that will be the one of the key in your autopilot design. Okay. Now coming back to that, this is one of the control law. So what is there? We'll say, okay, I have to control the position, I have to control the attitude. But how many inputs are available? I have 4 inputs and 6 outputs. So it's difficult to solve the problem. Then what I see, okay, people are doing that. I look into the literature and I say that people solve using the time scale separation principle. So it is like in similar autopilot, right? Stick, you are solving you are serving the different tasks. So in the mechanical or aerospace design, what they say that, see, your translation and rotational dynamics evolve on the different time scale. So when you are doing anything on the translation, you can assume that rotational is done their job. So there is whatever demand you will give rotational, it will feed you. But whenever you are doing on the rotational, you assume that translation is really constant, nothing is changing. So if you assume that you have two fully actuated systems, that is known as the inner and outer loop design. In the inner loop, you play with the attitude, and outer loop, that is your also guidance design, you will play with the position or guidance, how to change the waypoints and other things. So for stabilizations, that means you want to do the hover only. So what is there? Phi theta psi is your current attitude. Phi desired, theta desired and psi desired is 0, but I am putting here the phi desired, theta desired and psi desired. So if we have to do the attitude tracking, we can directly use this control law. We doesn't have to do anything. Then you have a derivative terms and integral terms. So you with our PID law, you know what is angular or angular acceleration is required, rotational angular accelerations, and if you multiply with the inertia, you will get that what is a rolling, pitching and yawing moment is required. Now LMN is there. Now this LMN you use with your control allocations, and you will change your PWM, that is duty cycle. And similarly, what we can do, now I see what is error in my positions. I use the D terms, I use the I terms, and I find the inertial acceleration. Now what happens in quad rotor? Say Z you can change using your thrust, but the X and Y position you change using the pitch angle and the roll angle. So this is some approximations. You assume that okay, this is like you can see that kind of omega equal to VR. Okay, although it's on not the velocity and no accelerations. So the acceleration terms I have used that G is your gravity vectors, and y double dot is your accelerations. So y it is related using this is a roll angle and pitch angle. And if you want to involve the kinematics, what I have shown few slides back, you get this relationship, and now this angle will be fed to your inner loop, because you have assumed that you have a two fully actuated system. Okay, you do not have to worry all about this. The reason I am telling that, you will be aware of that. Now like Pixoc type autopilot is available, we will look into that autopilot architecture, and these all control design are already designed. You have to only adjust the gain. Okay, so this is what I was talking about, the quadrotor hardware. So what is the hardware? This is STM32. It could be F1, F4, F7. I think this is work on STM F47. So what is there? You have 4 motors. So this is like you can say skeleton of the autopilots. These 4 motors connected with the battery because it's required the power. For control purpose, they are connected with the PWM, like means timer. So you have configure your 4 pin as a timer, and then you use S-bus, some protocol. So that will drive your 4 motors. So that means you hardware abstraction layer, some of the pins, alternate functionality of the microcontroller you will configure as a timer. Okay, then what is there? You have a telemetry. So in telemetry, usually we have a serial. So you use some serial protocol, okay, to communicate with the ground stations. That could be Mablink, and you have some pins you have to use for that, okay, for alternate function for serial protocol. Then you have your GPS. GPS is, I think, usually on the either I guess it is on the I2C. I might be wrong if I don't remember. So some pins you have to configure for the I2C. Then there are IMU. IMU is inside in this chip only. So IMU will be also configured on the either I think UART or I2C. So you should be aware of this all communication protocols. These are usually SPI, serial I2C, UART, UZART, and nowadays people start doing on the CAN also. The reason is that if your connection is large, then this data range could create a problem. So you can have a small microcontroller, you can put sensor, you record the data, and then from microcontroller to microcontroller you can have a CAN communications. So then you can have a buzzer, LED, and other things. And so once you know how many pin you should reserve for the SPI, I2C, UART, then you use hardware abstraction layer. You can use the Kelly or you can use the STM32 on software. You can generate this code, configure these pins, you clock, you enable that pin. But if you do this bare minimum programming, it will involve a lot of things. So you want some RTOS. What is RTOS? It's real-time operating system that will provide a lot of help you to do anything. So the reason why you require RTOS, so you can now directly can say that you can configure the direct pin calling the function. Okay, I want IMU GPS. Okay, you don't have to do the bare minimum programming. So what happens now? You have hardware. So this peripheral driver will be taken care by now RTOS. So what it does in RTOS, your sensor driver will tell, okay, I need I2C, I need SPI, give me the data. So it will configure that pin, okay, enable. Then it will read from this register that data, and then it will be published on the sensor driver. Then this sensor driver will take this data, and whatever if it requires the ECAP attitude or position estimations through the kernel, there will be this application layer, different application will be running that can subscribe to the sensor driver, and they can get the data of the GPS, they can get the data of the IMU. Similarly, when you want to run your timer, so you can ask your kernel, and then it will interface with the timer, and it will drive the particular pins or particular motor. So I am not going into the lot of details of the programming. I believe it would be discussed by someone. If it's not discussed, lot of open source sources are available. If you want to see, you can see Pixoc, you can see ArduPilot. Okay, and at IIT Kanpur we have also developed the Navic, and recently Indian government has launched this microcontrol challenge program, where they have come with the FPGA based board, that is a RT. So one is a Vega and another one is Sakti, and they have provided I think two type of RTOS. One is Jaifer and another one is I think free RTOS. And then you can have your middleware. So we are also trying to build our own autopilot for the flying vehicle purpose. So the hardware will be like microcontroller will be Indian. Software we are using the open sources, but then we would have our full control command, and application layers already we have written, but we'll be using. So that will be true design in India, in make in India autopilot. Okay. So right now what I am going to show, this is a 6 and 7 years back video. What I am talking about that. So that work has started 6 and 7 years back, and I could talk because that experience we have gained doing a lot of these things. So this is the reason I am showing that we have started from the very basic things. So if you can see, the autopilot was put in one dabba. Okay, if you look into the now the this DJI and the Skydio, you may not like it, but you do not reach to that level unless you start making your head dirty with the hardware and learn the basic things. So we designed autopilot, what I have already discussed with, went to each nitty-gritty. We have understand what RTOS they were using, Nutex. So it is one of the very good RTOS, I say. We have also explored the Chibios, another which is used in autopilot, and then we did the all basic things. Okay. So this was our work, and I have given the idea about this all things. So what is the limitation of conventional quadrotor? Apart from this autopilot things, we are also involved in the designing the quadcopter. So as I told, let's see, everyone use the all same 4 motors, because they buy from either from the T motor, they like Tiger motors or maybe KDE or local motors. Everyone using the same battery, lithium polymer or lithium sulfur. I don't think now people use lithium sulfur, but lithium ion. But some people get 10 minutes of the flight time, another one is getting 30 minutes, or maybe they get maximum 60 minutes. What is the difference? So difference is that how optimization. See, even the basic level you go that which gauge of the wire you are using, how light your frame is there. Okay, which type of sensor you are using. So all game is that in the minute details. But other way is round is that even you hit hard all the optimal things. For the optimal design, you may get around say 1 hour of the optimal time. But if you want to hit hard or you want to expand your boundary, you need another type of design, and the answer is that variable pitch quadrotor. So in variable pitch quadrotor, what happens? You can drive the vehicles now changing your pitch angle instead of the RPM. That allows me to design a gasoline based power plant. So what happens? Even my transmission systems become complicated. Now all the rotor will run on the single RPM. Okay, that I will control using some speed controller, and then the thrust I will change by changing the blade pitch angle. That means orientation of the blade with respect to the air. What is the advantage of using that? See, conventional quadrotor I cannot scale with the weight. The reason is that the torque required to change the rotational speed quickly exceed capacity of the motors. such design will give me that flexibility. Okay, so we are not the one who started working on this, but there are people even during the innovation of or invention of helicopter, that idea was explored, but it is given up. The reason is that the alternate design, okay, was that time got lot of funding. Okay, so maybe I may have a video I can share. So, but we are the one who has proposed the first time flight dynamics, systematic flight dynamics model. Okay, and then based on that there is a lot of work developed. So let me explain what is variable pitch quadrotor. So see, in conventional quadrotor you have a motor and this is a propeller which are fixed, nothing, just you change the thrust by changing the RPM. In conventional or the variable pitch quadrotor, now see the rotors are uh, placed with help of this assembly, and now what you do, see there is some rod which change the blade pitch angle, so you can do up and down through the servo. You can change the orientation of this, so that will change the blade pitch angle. So it's bit mechanical complex, but we don't have to worry. There are precise manufacturings are available, servos are available. Okay, so we can achieve that. Now we can look into the other control design also. That could be your back stepping or your dynamic inversion. Dynamic inversion is straightforward to do, but it cannot handle the like modeling uncertainty, because you are cancelling out everything. So even if slight inaccuracy is there in the cancelling, it may degrade the performance of your control scheme. So one of the approach is use the back stepping. So quickly I'll show you that back stepping. Do not worry about that. Don't get into the mathematical detail. And nowadays all video lectures available. Whatever you look into, whatever I am talking here, if I do not get, you do not get any, or you do not understand anything, if you Google it, or even if you search on the YouTube, you will get all lectures are available. Only things you have to go through this and you have to try to implement. So what this backstepping, the things require that the system should be in a strict feedback form. So like x dot equal to fx, or maybe x, or x1 dot equal to x2, x2 dot equal to fx plus gx plus u, and then you design the u. I am sorry, I am not using the board. I should have used, but that it has it didn't occur to my mind. Otherwise, I would have written here. So we choose one system phi theta psi, and the other one is PQR, and two subsystem in the position. One is we choose altitude Z and Z dot, because we can changing the throttle, we can adjust the speed, and another one is like X and Y. That is like using the phi and theta, we can change it. So we can write in this straight feedback form like this. So this is like you can say rotation, this is a horizontal, and this is altitude. Okay, this is a subsystems, and now we can design a different control law for this. So unlike a fixed pitch control law, now the control this control allocation is become difficult. Why it's become difficult? See what happens, as I told that when we design the mixer or control allocations, so you have some value of TLMN. Now you have to give the so this PWM. Okay, with T minimum what will be the pulse width, and T max what will be the pulse width. Now we have this CT, and the relation between TLMN and CT is non-linear. Okay, so whether we have to do the curve fitting or we have to generate lot of data and fix it, that is a difficult. So there are different ways. We have also explored many things. Here in this talk, I am taking you that okay, to make life easy, I am doing the dynamic control allocations. So I have introduced the one loop. That is, I am telling that there is actuator dynamics, and actuator dynamics evolves like that. So whatever you give the UID, it is like a first order your differential equation, or first order like a delay function. Whatever you have a background, you can understand. It takes some time to track it. Using that, you introduce this dynamics and you use that, and you will get now this is this equation cities, and now you can invert, you can get the cities, and you integrate the cities, you will get the current value of the cities, and then you give to the your mixer as you were giving the earlier. So this is the hardware. So this is a Pixoc board. You can see ASC. This is a motor which is a driving the, see, this is a like a electric powered variable pitch quad rotor. The reason why we have done the electric propelled variable pitch quad rotor is that we wanted to gain some confidence before to move to gasoline. So you can see the gear and pinion systems where how it's the rotational motion and translation motion, other things is converted. So this is a servo is there. Okay, so it's running servo and pitch varying mechanism. So this we have brought it and adjusted something. So this frame was available. So but we have adjusted some things, manufacturing edit we have done, and this is a quad rotor. And then what we have done, we have implemented our backstepping control. So first we look into the how pitch tracking is done. So manually we have given the pitch command and we see that tracking is good. Then we have given the roll command. So it's also follows good, and you can see the value is very small. Okay, although it's in the radian small, it is good. Then we did a yaw tracking. So that means in all three channels, pitch and roll and yaw, there is a good attitude tracking. After doing that, now we have come into the positions. We have started from the ground. We'll take off and go to the waypoint 1, and then we have given the sequentially 4 waypoints 1, 2, 3, 4, and from here we start blending. So this part of the trajectory is not designed. Waypoint 1 to waypoint 4 is designed. Okay, so this way we can see the what is a desire and the what is a given. Okay, so you can see position, and then there is an end position. Here only we'll end. So this was a design. I am sorry, this was not a design. That's why you don't see the black things. So this is the whole thing. It's so that how phi, theta, and psi changes, and the reason this change you see after reaching the particular waypoint, we are changing the heading. So that means we are not doing the coordinate turn. We are just changing the heading and we are moving into the different directions. So this plot involves little more understanding or little bit more time to understanding, but I am not spending time because of the paucity of the time, but I am happy to discuss if someone is interested. And now you look into the so like a simple rotor, we have a variable pitch. So it can do whatever the conventional quadrotor was able to do. With doing this, now where we have come to the engine base. So engine base quadrotor, what we have to change everything, and the whole thing is hard is that we have put the engine here. So whole transmission system was designed and design is optimized also. And now you see the blade does not have a pitch because we are changing the variable pitch. Okay, so we have put the tank also, and this is like a Pixoc. You can see this is a battery and this is a transmissions. Okay, and there was another prototype. So we have used two types of the quadrotor. One is based on the torque tube, that is more accurate, and the alternate or the other one is based on the this pulley driven. So even some manufacturing defect or manufacturing alignment is not proper, you can also survive. Otherwise, torque tube require the precise manufacturing. Okay. So this is so transmissions. Okay, and you can see that bevel gears. Okay, how this. So all the optimization is done. How to choose the gear? What is the gear ratio should be there? How many teeth are there? So this is a torque tube based design, and this is like a I have done that pulley system, right? Belt driven. So this is a you can see that one is a center engine. It is a driving the main, and then you have this the 4 subsystems. This is for one motor, another motor, other motor, and the other motors. So in this way, but see, if you control the speed, you will control here. So some of the variation due to the belt is there in the speed will, and if it result in the thrust, we are expecting that to handle through our control design. So RPM has been also mentioned. And then what, through the optimization, we have got the part of the each part. So that includes the which is engine. We have used the Genona engine, this transmission structure, avionics, blade, fuel tank, fuel, servos, and total weight. So this is a percentage of weight, and we have done for both vehicles, and look that value is very small. And if you have to win the game of the quadrotor design, okay, when I say game win, if you have to be you want to be a best in the, so for each part you have to reduce the weight, okay, and you have to get the optimal weight. And if you can, each gram of the weight reduction will give you some advantage in endurance, maybe few minutes. So whole fight is designed this approach, or whatever I have told about conventional quadrotor. See, quadrotor is now become the state of art. Anyone can do. You can do. It's not a big deal. And if you do the Google it, or look into open source, easy to design. Like there are autopilot code is easily available, design is available, BLDC. See, motors, we are not manufacturing the motors, we are not manufacturing the servo. Only things what you have to do, you have to bring the some tubes, you have to connect it. And see, autopilot board also we are not designing. We are not designing the any autopilot bomb from the sketch STM30 microcontroller. We are not designing anywhere. So most of things you brought out from the market, and you assemble it and start doing. But some people are getting endurance of the order of hours, and if we design, we may not get it. So each and part you have to understand from the each part of design, that include hardware design, electric connections. It is a mechanical design. Although even you do not have a transmission, if you do this proper, then only you will get the significant advantage in terms of the endurance, and that product will have a value. Otherwise it will have only, you can see a pedagogy or like teaching, or maybe some, if you are demonstrating on the some research things that have a heavy value. Otherwise flying quadrotor is it's become a state of art. Okay, so with that, I'll show that we have start testing. So it was our first flight, and we had a confidence in this vehicle, because we have already flew the electrical one. So when we start flying this gasoline one, we were pretty confident it would work. But now you see that. Okay. Although I told that you can do everything, but if you do not make your hand dirty, these things can happen. See, okay, where will you put the autopilot? Whether since it's an engine, so vibrations are entering into your sensor or not. If you are entering into the sensors, it will make your readings of IMU bad. And if you are not filtering out, and mechanically or maybe from the signal processing point of view, it will get into your autopilot, and everything will be gone. So from mechanical perspective, as well as from the your autopilot perspective, you have to be careful about that, and you will not learn until unless you do it. So we also started from the gate. We again came to our workshop for our lab. Now we have tied it and we change uh, change something. Okay? It is point by point. We have started whether we have to look into the autopilot, look into the control, and see that so development happens so that time, then you can see that. So finally, it's a lot of effort to fly. Now it's you can say really we can fly. Maybe we have not center that is a conventional formula in terms of each translation also, that is not shown in this picture. So what now I want to show that, see, I have shown the engine quadrotor, but I want to show helicopter. I don't want to discuss all mathematical model and the control here. The reason is that it is very involved and we have a limited time, so I'll quickly talk about the application. Prasid, how much time do I have if you are available? Maybe another 10-15 minutes?
Yes, sir. Yes, sir, you have.
Okay. So what we have done now, you can see it's a kind of magic. You are flying upside down. Yeah. So in the beginning, I have shown some video where we use this geometric control. So this now attitude is defined, all defined, and now we flip the switch, so we can change the blade pitch angle, and not only on the roll axis, we can do on the different pitch axis also. See, okay, flip the switch, it will start flying. The reason we just not wanted to show that it's a 3D flying. What we wanted to see that our autopilot is a robusting up. That means even it's flip, see, if air flips the vehicles you are down, my autopilot will able to handle and bring back into the in original position. So we were able to do multiple roles and other things. So it requires advanced control and the autopilot knowledge. Okay. Now I'll show you the different type of the quadrotor. I don't know whether Professor Sau yesterday talked about this or I don't know, but this is a like a fully actuated tilt augmented quadrotor helicopter. The advantage is that in compared to, see, we have talked about two different quadrotor. In this quadrotor, what happens, your motor tilts also. So I have talked about the thrust vectoring. So you have the flexibility of thrust vectoring. So why do we want such quadrotor? We require such quadrotor because, see, if you are following the any person, human tracking and other things, and if you have a camera as person or vehicles or object is moving, you need to adjust your orientations in order to track it. If you do with the conventional quadrotor, then see the position and camera tracking will mix it up. So to decouple it things, you use the like gimbal. So you place in that, and the gimbal adjusts based on the how the object is being moving. So in these vehicles, what you see, you want to save the weights. So you don't design the separately gimbal. The quadrotor, the frame can stay as it is, okay, but your so that means the vehicle does not have to turn for the traveling forward and backward. This rotors, what it is showing, they can tilt in front direction or side direction or moving forward and the sideward. So this is like we have seen every rotor generate thrust, and now the thrust can be tilted. So by tilting another servos, so obviously it comes with some added cost. What is the added cost is that we are not using the gimbal, but now we are using the additional sensor, that is servos. So these are 4 servos, and these 4 servos control the direction of the thrust vector. So we have used the quaternion. Now quaternion using for the quaternion is that we wanted to be more mathematically accurate and want to leave with the less error in the autopilot. So this is a quaternion basics. So it is a, you can see high order the complex numbers. So you might have seen I or J earlier, only a single axis like complex number. So you have a now complex number with I, J, K, A. So it's like a kind of vector algebra, but it's not a vector algebra because, see, it's I square, J square, K square is -1, and you don't have a cross product here. See, I, J equal to K, and but very similar to that. Or so it has a 1 scalar part and 3 vector part. Using that, we represent the attitude and used in the attitude control. And good part is that estimation is also done in the quaternion, so you are not converting anything. So you do not cause, or the system does not gather, or the error does not seep into the system while converting anything. Okay, straightforward. So this is some relationship how the quaternion. So we have seen the 3-to-1 rotation earlier. So here how does it comes and how does rotation matrix come? This is a quaternion attitude dynamics is present. This is the Euler equations. So and now what we have introduced the two additional degree of freedom, thrust and vectors. So is it possible that we can rotate all the thrust vector of the all four rotors? But for simplicity, we have constrained that the opposite pair will move by the same amount. Okay, so the 2 degree of freedom is increased, so we have a total 6 degree of freedom. So now we can control translation and rotational separately, and this time scale separation principle what we have assumed earlier is not required. Okay, so this is a like control inputs. So that mixing how we have to do, it's a bit tricky because the angles is involved, but it can be represented like this. Again here cos alpha that is involved, but we have to live with that. Now attitude control is like just a PD control. You are computing what is the error in your quaternion. So it follows different algebra. It doesn't follow the simple like vector algebra. It is a like complex number. So error you are calculating like that, and then the angular velocity you compute. So they are defined in different frame. So you have to use the rotation matrix, and you can use the simple PD type controller. And then similarly you can do the position control, and now T1, T2, T3 will give you the required force in the X, Y and Z direction. See earlier we have computed the acceleration in the X, Y, Z. So right now or in this slide we are computing the force, and that force we are telling that this force is required you generate into the body frame. So using the this quaternion we are using the rotation, and then the control allocation is done. So that will generate, see you have given the body force here. Okay, and then you have this, you do the allocations, you will get this, and this is like a first flight. Okay, so again this would have been done 3 years back, and the first frame, and we have used balsa wood. Balsa wood is a very lightweight, so we wanted to reduce the weight, so we used the balsa wood and designed the frame that was able to do the basic function. And this is a like plot. You can see earlier I have shown. So this is another work using this quad rotor. We have done the tracking. Okay. So if you see usually tracking, you need a deep learning algorithm. So in deep learning algorithm, what happens? You need a GPU. So I'll come back to that part. Let it get over. Explain. So we have used Arupo marker. So this is like you can see binary image 010 grayscale. So they are easy with the autopilot. You can process, or like we have used NUG code, which is easily can do. Otherwise, if you are doing the conventional image processing, you need a CNN type of things. Okay. So this Arupo marker is easy. So we have used a free Arupo marker. So the reason we have used this combination, if you are at a different altitude, you at least you are log to one of the Arupo marker, and the quad rotor. See, my student is saying that he is not controlling the quad rotor. We have put this board into on the jeep, and then the quad rotor is tracking. So it's generating the speed by tracking this Arupo marker. It's generating the forward speed. So right now the vehicle is moving with the 15 kilometers per hour, and it goes and land on the jeep. So I was the behind. If something's wrong, goes wrong, we can confirm. And the student was now sitting in the car. So we have now moving with the 20 kilometers per hour. You can see what the frame is stationary. So we have done more speed also, but I'm sorry I don't. So what I want to see, see if you want to do the like the human tracking, okay. So what you have to do, you need some like camera, okay. After camera, although camera is lightweight, but it will come with the added, you can see or its complication. Added complication is that now you have from the given frame you have to identify the human. maybe multi-object target or single object target tracking. So if you are doing the tracking, there are two parts. One is detection and another one is a tracking. So for detection, you can use the conventional computer vision, like you can find the features based on the key points, and you can have features like a shift. Shift is popular because it's an invariant from direction, other things, but you can have a hawk, or you can have a Harris detector or some things where you make detect the line and edge, and then you try to make it out, and it's usually difficult. So what is the advanced way? You use the convolution neural networks, so that you learn from end to end learning. Even what is your filter, you learn it, like this edges and other things. So lot of weights available. When I say that, see, you have a conventional neural network. So these are the deep layer neural networks, and to run on the simple board like RPi or maybe NUC, these algorithms cannot run, and you need a GPU. So there are GPU board available which you can run, but then they are power hungry. So you need some tiny tiny type of network that could be YOLO 3 tiny. So they are very light in the weight and still can run on the mobile platform. And there are a lot of research going on this, and my group is also performing that. So you can learn the deep neural networks, okay, like as happened in Skydio. If you look into the Skydio, I think, I don't remember, it has a 6 or 12 camera, it can track the people. So you need the state-of-art sensor and the state-of-art the tracking algorithms, which is not power hungry and very efficient. Okay. The other part, before I end, I'll talk a little bit about SWARM system architecture, which my group is also actively working. So in the SWARM, one thing is that you maintain the relative formations. Everyone is doing that, is a demonstration purpose. But what you can do some useful research also, like you can deliver some, you can identify, like now you can have a camera. If you are doing search and rescue missions, you can identify what is people needed, or you find that someone is trouble or rescuer and you help him to guide, okay, or you inform your ground stations, you have a video transmission or maybe photo transmission, and your ground station manager take a decision, and then you serve whatever the way possible, okay, delivering medical package, delivering the rescue material and other things. So anytime you talk about the SWARM, one is a platform, vehicles, another one is autopilot, the third one is communication, ground station and vision. Okay, so these are like a basic components you require. So this is a simulations of the 50 vehicles. So I am quickly going because of the time constraint, but whatever I'll give the idea. Okay, so this is a like algorithmic part. You can maintain the relative spacing. So that has been solved. So now coming back to the software. Okay, software is that, see, your vehicle is there, and this is a, you can see running with the, what you can say on the your vehicle on the your on the ground system. So what happens, see, we can have a one-to are running the rows. So you have been introduced on the rows, you have mission and path planning, whatever is given, you path the plan. Then you see the SWARM health monitor. So you have a communications module, and that could be your star topology or mesh topology. So you have some communication module available, like you have a telemetry unit or micro hard unit. So that is talking with the ground station. It says, okay, I am afloat or I am alive in the sky. Then you can have a object detection and classification. Anything is sent by the vehicle that you run, because on the ground station you can have a powerful GPU, and you can quickly run these algorithms and can make a decision. You can do the video processing, and you can have a real-time mapping systems, and we can do the network optimization. That means antenna, see, for connectivity on the ground, we can track the vehicles and can orient the antenna, but we may have to have a multiple antenna for that purpose. Then from swarming, we can have a different swarming like algorithms. Okay, that we'll see in the next slide. So this is a edge system. Okay, edge system that would be on the vehicle itself. So what does it will have? it will have a companion computer. See, you don't want to, you want some fail-safe features. So what will you will have Intel up board or some GPU board. So that will be running your ROS. It has been connected with the camera. So it may do the basic processing and maybe rest of things, or it will give it make the decision and will inform our autopilot. So autopilot will be responsible for just for waypoint tracking. Okay, and it may do basic things. So if you are doing the vision processing, it will be done on the companion computer. So that is there, and they will talk through the some network. So it may not be possible that all the vehicles are directly connected with the ground stations. There could be a relay, or they are connected from some other vehicle. So this networking is involved, and there is this, you can see mesh network come into the picture. So this is a software. I don't go into other, but now I want to show the video, and you can see that we have a 4 node, and the basic idea, it's demonstrated what I have shown the vehicles. One is a leader, node 1 is controlled manually, and all these 3 is trying to following this. Okay, so they are making a triangular or triangular type shape. Okay, and the follow make the relative distance. So based on this, this position has been transmitted to the all the follower, okay, through the mesh network. So we have created mesh network using the Wi-Fi. So you can have a very quick data transmission. If you do not have a Wi-Fi, you have to rely on the onboard telemetry, and there only this networking come into the pictures. And based on the position of the leader, they will find what is their relative position, and they update, and that has been sent to the individual autopilot. So this is, I think, so I do talk about the this what it is, that's the suspended load system, where you cable will suspend the load, and so this is a basic demonstration. So in the what happens to quad rotor, this is a stabilization, and now this will be disturbed, and you can see that, okay, whenever it's disturbed, quad rotor moves and they try to stabilize them. Right. So this is a like trajectory tracking. Oh, for some reason the video has been inverted, and I have never corrected this slide. So you can see that it can be tracked, but if this happens, this is a magic. Quad rotor in ground and the load is in the air. So the reason why I am showing this, to get motivated to do this all things, and then we can do this conventional robotic application, what I was talking about, path planning. So we have a RGB camera. Okay, this is like a Z camera. You have a stereo, and you have a color information also. We have created a map on the whole environment. So quad rotor is flying here. So you would have seen such video in the YouTube or maybe in some talk, and the whole map is created. Okay, so this is the whole idea, and that could be, so this could be useful. Human tracking is also done. So I don't have a maybe that video, but this is in the ROS. I think you might have introduced by I think ROS and Gazebo by Ajit might have talked. CNC quad rotor is following that. So now we are trying to implement this in real hardware. We are using this YOLO deep learning, CNN YOLO 3 and YOLO 5. But see what happens, this camera gives only the good information up to 10 and 20 meters. So if you are following some things, it will make a sound and he may hide something. So we have to come with the maybe high optical zoom camera and come up with the right set of hardware, so that serve our purpose. So this is a like indoor localization without GPS. So what we have done, we are using the ultra wideband sensor. So what it does, it is on the time of flight base, it's give the range, and now you don't need a GPS. Without GPS, so it get the ranging informations, and you get if you see this, it is ultra wideband based sensors. So it get the accurate range information, and indoor we have get the accuracy up to 10 centimeters. So unlike into the motion capture systems, one is Vicon and optical axis or something is there. This is a pretty cheap, and this is a like we have created our own real-time positioning systems. When we have created, we have taken the decaware sensors, okay, that gives, and that sensor we have designed the PCB. We have developed our own sensors, and that will give in the real-time position of the vehicles. Even it can give the yaw angle, and it is a damn cheap. If you want to buy from the motion capture system, it may cost you 1 or 2 crore. The whole unit what we have developed, it may cost you 5 to 10 lakh rupees, and it gives the accuracy of the 10 cms. And unlike the motion capture system, it can work both in indoor and outdoor. Okay, so what we have done, if you have a 4 or more sensor, it do the triangulations, it find the position, and the position is fed into the your EKF, and you will have a trajectory. And this project is done like supported by MHI Japan. So I have done for the Japan. So summary, I have shown you the basic quadrotor. Then I have shown the advanced type of, or maybe different version of the quadrotor, variable pitch. It's a different variant, engine powered and then tilt powered. And I have discussed lot of applications. So I did not go into the lot of details, but basic idea I have given about the autopilot, how hardware works, how flying things work, and I have talked about the various aspects you see into this. And we do not only believe in the indigenous development, we believe in the design in India, made in India. With this, I would like to thank to all, okay, for listening me. If you have any questions, I will be happy to answer.
Yes, sir, there is some question in the chat box.
Okay,
One
so
is Pramod Jadhav is asking that can we use fractional order control method for precise control?
So there are a lot of this fractional order control is there. So I don't know how do you implement in hardware that. Okay. So see fractional order code. See if I have a PID controller. So autopilot implements algebraic equations. The moment you give the fractional order, would you approximate that fractional order by how? Some math library is available. If it can compute, you can implement that. Okay. So we have not done. If you have answer for that, fractional order can be implemented. Okay. Because see, if you are doing in simulation, you have to integrate the differential equation. But if you are working on the hardware, you don't have to integrate, because if your flying vehicle is there. So only things you have to compute your control law. But control law, whatever you are doing, it should be mathematically computable. Okay, and it should be in the real time. Okay. I can't see chat. I can't see chat box, or maybe it's only you can see, huh?
No, sir. You can also see, but might be in your setting. Yeah, it's participant. Near participants, you can see the chat.
Okay, so no anywhere you can, if you can read the question.
Yes. Any other questions from participants? You can raise your hand also, so I can unmute if you want. Any of you?
And I am happy to share that I have done some work jointly with the Prasid on this quadrotor. So we have now done the computational work with using sliding mode control. Maybe if you are interested, you can contact Dr. Prasid, and maybe we can look into how to implement it.
Okay, sir. Yeah, if no more questions, then I will simply go for the vote of thanks.
So there is some mega, I think some. So yes, you can unmute Mega, or please unmute her.
She has raised the hand. I'm not able to see.
It's a Mega.
I didn't saw any hand is raising.
So, Megha, can you raise the hand again? So Divya could see. Okay, there is a message. Megha Trivedi. Oh,
Okay,
I
by
don't know.
mistake, she done, I think. Yeah.
Okay, that's all right.
Okay, sir. Yeah.
Mm.
Okay, sir.
Mm.
Which book to follow for learning ROS? Rose?
Ross is there is a nice. Ajit might have told you your alumni, but there is a nice this wiki tutorial is there. So there you don't have to follow. There are books and there are a lot of updates is there. Now see you're looking the book earlier book, now Rose Indigo is there. So better you follow the wiki. Okay. Wikipedia. When I say wiki, it's a Wikipedia tutorial.
Any other questions? Okay.
Mm.
Thanks coming.
Okay, you can thank me and then.
Yes, sir. On behalf of Department of Electronics Engineering and RIT, I would say really thank you, sir, for the wonderful session on this autonomous multi-copter UAVs. You have shown us the various interesting videos, so I'm sure like participants get really benefited and motivated with this session and shown their interest for further work in this. Okay, so my sincere thanks to you, sir, from all the participants also for your valuable time. Your valuable time and come here to give us this session.
So it's my pleasure and thanks to the audience and thanks to the students, and I wish all of you best luck.
Thank you, sir. Thank you so much.
Okay, bye.
Okay, yeah. One note for the participants that please log in with your proper name. As we have earlier mentioned that there is no separate attendance